Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures on computer architecture. So, we have been looking at various aspects of computer architecture. So, we looked at the instruction set architecture, how instructions are organized. We also looked at details of the control unit. Now, we have started looking at some of the details of the memory unit. So, what we have covered with respect to memory units so far is that we have just looked at different types of memory devices. Essentially, we looked at random access memory and different types of read only memories, which are EPROMs, EEPROMs, flash devices and so on. So, we have just looked at some of the characteristics of these devices and how they function. So, what we will be looking at today is that we will look at how these different types of devices are organized in the form of a hierarchy, a memory hierarchy as it is called, and how this memory hierarchy is useful in terms of efficient access and in terms of speeding up the entire process. So, we will look typically specifically we will today look at something called caches. So, that is what we plan to do today. Okay. So, let us start with the memory hierarchy. So, let us look at this picture here. So, if you look at the different memory devices, so to say, that we have, you can see that right inside the processor itself we have the registers and the something called a cache, which is typically located very close to the processor. Now, this is called as the primary cache or the L1 cache it is referred to, and then we also have something called a secondary cache or an L2 cache that we have. Then you have the main memory and then you have the magnetic disk or secondary memory as it is called, magnetic disk, optical disk and so on. Okay. So, if we look at in terms of size, if you look at what is the size of these different types of memory devices that we talk about, registers obviously we know are small ones. Typically we talk about 32-bit registers or 64-bit registers and so on, and the number of registers may be limited or it may be fairly large, but typically not more than say 512 registers or 1000 registers. So, the total amount of memory that we have in terms of registers as such is normally small. Okay. So, if you look at it in terms of size, therefore, you can see that as we go from registers to magnetic disk here, the size will increase. Okay. So, registers are small memory devices, small units of memory as we can call them, and then caches are slightly larger than that. Secondary cache would be larger than that, main memory would obviously be much larger, and then magnetic disk will be very large. If you look at speed you will find goes in the reverse direction. Registers are the ones that can be accessed really fast, and the L1 caches, these are the ones, primary cache is the one that is accessed little slower than the registers. Secondary cache may have a speed which is even less than that, main memory even lower than the secondary cache, and the magnetic disk would be the one that is the slowest in terms of speed of access. And if you look at the cost also you will find increases with the speed. So, a faster an access, the cost per bit will also be high. So, this is something that we need to remember. Size you can see is increasing as you go from registers to magnetic memory, but speed and cost will increase as you go from secondary memory to registers. So, registers obviously will be the fastest, but they will also be the most costly, they will be costliest in terms of the memory devices that we are looking at. Okay. So, keeping this in mind, we need to understand what can go where and why this kind of a memory hierarchy obviously is necessary. Okay. So, this is what we need to look at. Now, what is this cache that we are talking about? Okay. Now, so far I said there is something called a cache that is used. So, what exactly is this cache? If you look at what exactly the cache is, it is just, you can look at it as some very special type of memory and which is normally implemented on the processor chip itself. Okay. So, we call it as the processor cache, okay, and the primary cache. Sometimes you have both the primary cache and the secondary cache also implemented on the processor chip itself. Okay. These are variations that we have today, but you can generally look at it as a special type of memory which can be accessed much faster than your main memory. Okay. That is what we need to look at. So, then coming to the main memory as such, we already know how the main memory is implemented. We already looked at devices that are used for main memory. So, these are implemented using SIMs, and of course they are much larger, okay, but slower than cache memory. Okay, so this is the point to remember here. Next level of course is the magnetic disks, which are huge but inexpensive storage. So now that we have this, what is it that we need to keep in mind? What we need to keep in mind is that the speed of memory access is critical. Okay. So the idea therefore that we use is, you bring the instructions and the data that needs to be used as close to the processor as possible, so that it becomes faster to access the instructions and data and execute the instructions from the processor. The processor is the one that is going to execute the instructions. It needs the data. So the instructions and the data that it needs to execute should be brought as close to the processor as possible, so that it can be executed faster. But of course we said the sizes of these devices will be smaller. Okay. So what you bring in obviously will be limited. So how do we manage this? How do you bring something which is resident in your magnetic disk or your secondary memory? From the secondary memory, what do you bring to the main memory? And from the main memory, what do you bring to the secondary cache, and then the primary cache, and then to the registers, and then execute it? Okay. So how do we manage this entire hierarchy? Now why do we want to manage it? You can see the reason basically is that we want higher speeds of operation, but the cost of operation is high as the speed increases. So naturally I can't put I can't make my primary cache very large, so that all the data and all the instructions that I want can be fitted in there. Obviously if I were able to do that, then the speed of access will be excellent, but what would happen to the cost? The cost also will become very, very high. So which is why we can't afford to have a very large primary cache or a secondary cache. So which is why we need to have this kind of different types of devices, have a memory hierarchy, and worry about bringing data and instructions across these levels of the hierarchy. So initially let us say it is resident on your secondary memory in your hard disk. From there, when do I bring it into the main memory, or how do I bring it into the main memory? Where exactly do I place it into the main memory? Similarly, from the main memory, when do I bring it into the secondary cache or the primary cache, and then from there how do I execute it? So this is the major problem that we normally look at when we are looking at how to deal with this memory hierarchy. To summarize this technology that we just talked about with respect to these different devices, right? The static RAM and the dynamic RAM, which are used for the memory devices, the speeds will range from 0.5 nanoseconds to 2.5 nanoseconds. Okay, this is the access time. So this, to access one word from the static RAM, it may take about 0.5 nanoseconds to about 2.5 nanoseconds, and the cost you can see is around this $2,000 to $5,000 per gigabyte. Dynamic RAM, DRAM on the other hand, has a slower access than this, 50 nanoseconds to 70 nanoseconds. The cost of this memory, $20 to $75 per gigabyte. You can see that there are about 2 orders of difference between these two. Magnetic disks, if you see, 5 milliseconds to 20 milliseconds. You can see that the speed of access is much slower here, okay, but the cost also you will find is much less, 0.2 to about $2 per GB. So again you can see that there is a major dip in the cost over here. Okay. So what is the ideal memory that I want? I will need the access time of the static RAM, but I want the capacity and cost of the disk, of the magnetic disk. So if I get a combination of these two, or effectively if I am able to get a combination of these two, that is what we are looking at. Okay. So that is what we want to achieve with the help of this memory hierarchy. So we will start first with what is the idea that is normally used to use this kind of a memory hierarchy. One of the ideas that is used is called as the principle of locality. Now this is a very important concept that we need to understand, because this is what is primary to the working of the entire memory hierarchy mechanism itself. Okay. So what do we mean by this principle of locality? So what we find is that when our programs actually get executed, the programs actually access only a small proportion of their address space at any time. Okay. If you observe the way programs get executed, this is an observation that you will see, that when a program is executed, it typically accesses a small portion of the address space at any given point of time. Okay. So which means there is some kind of a locality, there is some local area that is being accessed again and again. And if you look at this locality, you will find that this locality can be looked at both in terms of time and in terms of space, okay, and in terms of the addresses that are accessed. Okay. So if you look at it in terms of time, okay, what we call as temporal locality. So what do we mean by this temporal locality? That is, what we say here is items which are accessed recently are likely to be accessed again soon. that is if an instruction which is there at a particular address has just been accessed, it is likely that it is going to be accessed soon. The same address is going to be accessed soon again. So, examples of this of course are, if you take for instance, many programs that we write will typically be running in a loop. So, when you have a loop, the loop gets executed again and again. So, the instructions which are there in the loop are going to be executed again and again. So, if a particular instruction has been accessed within say 10 instructions which are there in the loop, after the 10 instructions are over, again you will come back to the first instruction. So, the instructions in a loop you can see will have this property of temporal locality, that they will be accessed again and again in time. Okay. So, maybe after 10 instructions, maybe after 20 instructions, but it will get accessed again. Okay. The same thing is true about induction variables. For instance, let us say you have a loop variable. Okay. So, you have a variable that is being incremented at every loop. Okay. So, I equal to I plus 1. So, I plus 1 is going to get done at every iteration. So, when that happens, that data is again going to be accessed during every iteration. So, again in terms of time, within a short amount of time, that same variable is likely to be accessed again and again. Okay. So, we are able to identify that some data and some instructions will be accessed again and again within short periods of time. So, that is what we call as temporal locality. Another type of locality that we talk about is spatial locality. So, what we are talking about here is that items or addresses which are near those which are accessed recently are likely to be accessed soon again. Okay, that is, if I have just accessed a particular memory location. So, let us say I have accessed memory location 1000. Location number 1002 or 1001 is likely to be accessed immediately afterwards. Now, why do you say this is going to happen? Typically, this will happen because, especially with respect to instructions, most of the instructions you will see will have a sequential access, right? Because instructions are located sequentially one after the other. So, if I have executed one instruction, then I will typically be picking up the next instruction for execution, which means the sequentially next address, the instruction which is there in the sequentially next address is the one that is likely to be executed. Okay. So, sequentially next instructions are going to be picked up. So, when we say that one instruction has been picked up from a location, next instruction which is there in the next location is also going to be picked up immediately. Okay. So, this we call as spatial locality. They are different instructions, but they are going to be accessed soon one after the other. The same thing can be said with respect to some type of data. For instance, let us say we have an array that is being accessed. So, let us say we are doing some matrix computation. So, okay, so we have an array of data. So, I have A of 0, A of 1, A of 2 and so on. So, if I have accessed A of 0, quite likely that I am going to access A of 1 immediately after that. So, data also, we can say that data which are placed close to one another, especially when you have these kind of arrays, they are going to be accessed soon. Okay. So, we have these two types of localities, temporal locality and spatial locality. So, spatial locality, we are talking about different data or different instructions being accessed, but they are nearby each other and they are going to be accessed soon after. Temporal locality, it is the same data or the same instruction which is going to be accessed after some amount of time. Okay. So, this is temporal, this is locality with respect to time. So, it is temporal locality. This is locality with respect to space. So, we call this as spatial locality. So, it is these two observations of locality that we see in programs that we try to use in our memory hierarchy. Okay. So, you can see what is that we can actually use out of this. So, how do we take advantage of this locality that we have? So, what we do therefore is you store everything on the disk. Okay, that is where everything is to start with. But the recently accessed and the nearby items will be copied from the disk into a smaller DRAM memory, which is your main memory. Okay. So, remember our hierarchy, we start with a disk at the lowest end and then we have the main memory. So, what we do is the temporally related data, temporal locality data and the spatial locality data. Recently accessed is your temporal locality data. Nearby items will be your spatial locality data. So, you copy the recently accessed and the nearby items from the disk to the smaller DRAM memory, and then from the DRAM memory similarly you will access you will copy the most recently accessed and nearby items to the smaller SRAM memory and the cache memory which is attached to the CPU. So, your typically cache memory is implemented using SRAM memory. So, from the DRAM we move it to the cache memory. So, from hard disk to main memory and then from main memory into cache, and the cache is the one that is attached to the CPU. So, the CPU will access the data from the cache. From the cache, of course, it will transfer it to when an instruction gets executed, it gets transferred into a register and it will access it from the register. Okay. So this is what we propose to do. So use the locality of reference, take advantage of that and work with the memory hierarchy. So we'll take a short break now and come back and continue on this. Welcome back after the break. So we were just talking about how we make use of the principle of locality in order to use the memory hierarchy effectively. Okay. So we will take a look at what we actually do for that. So as I said, you have the processor, then you have this cache memory, okay, or the next level of memory as such, and then a larger level of memory here. Okay. So what do? Essentially you transfer data from this larger block to this smaller block. Okay. This is a faster access. So from here I will transfer it to here and from here to the processor. Okay. And the way we do it, copying of the data, is normally done in terms of blocks, okay, or lines as they are referred to. Okay. So when I say a block, it means that it could be multiple words. So a block is a unit of copying. Okay. When I copy data from a lower level from the hierarchy to a higher level in the hierarchy, okay, I will be copying a block of data, which would typically be multiple words. Okay. And when a processor is accessing data, it will first check in the higher level of the hierarchy. Okay, that is in one which is closest to it. So let's say processor, let's say this is cache and this is main memory. Okay, to understand things, let's say my processor is here, this is the cache and this is the main memory. So what the processor will first do is it will first check in this upper level, which is the cache. Is present in the upper level, we refer to that as a hit. Okay, so hit indicates that the access is satisfied by this upper level. If the access data is not present here, then we call that as a miss. So we talk about a cache hit or a cache miss. Okay. So what do I mean by miss? This means that the data is not here, and if it is not here, what do I need to do? I will have to copy it from this lower level to the upper level. Okay. So the data which is over here, one of these blocks here, one block will be moved from here to this upper level memory device that you have here. Okay. So if I have a miss, therefore we need to copy the block from here to here, and when I have to copy it from here to here, there will be some time taken for that. So that is called as the miss penalty. Okay. So when we talk of a hit, there is no penalty because directly it is there here, so I will be able to access it directly from here. Okay. If there is a miss, then I need to copy the data from here to here, so that will take extra time. So that is called as a miss penalty. Okay. So there are two terms that we use here, right? So hit ratio and the miss ratio. So what is this ratio and miss ratio? Hit ratio is the number of hits that you have over all the accesses that you do. Let's say you do 1000 accesses. Out of 1000 accesses, if I get 900 hits, 900 times I find it in the thing, then I say my hit ratio is 900 by 1000. So 0.9 will be my hit ratio. And miss ratio will be number of misses per divided by the total number of accesses. So what do you have here then? So the same example if we take, we had 1000 accesses, 900 were hits. So obviously 100 would be misses. So the miss ratio will be 100 by 1000, which will be 0.9, or you can also look at the miss ratio as 1 minus the hit ratio. 1 minus 0.9 hit ratio is 0.1, that will be the miss ratio. Okay. So miss ratio is related to hit ratio as 1 minus hit ratio. Okay. Now once you have got the data copied into the upper level, from the upper level it is sent to the processor. Okay. So you can see that when I have a hit, my access will be faster. When I have a miss, the access will be a little slower. If you manage to make sure that the hit ratio is quite high, which means that most of the times I will be able to find the data here itself, then my overall accesses will be from the upper level and therefore they will be faster. That is the idea we try to use. And given our spatial locality and temporal locality, our assumption is that once you brought data into the cache, you are likely to find it in the cache most of the time, and therefore you will be able to get a faster access. Of course, it is not there in the cache, we will always go back here and transfer it from here to here. Okay, this is the idea that we use. So remember these terms: hit, a cache hit and a cache miss, and we talk about a hit ratio and a miss ratio. And when you have a miss, we have something called a miss penalty, which is the additional time taken to transfer data from the memory to the cache. That is what we need to remember. Now coming to the cache, okay, what does this cache memory actually look like? Okay. Now typically what you will have in the cache is there are different blocks of data that would be there in the cache. Now each, you can look at the cache as divided into number of blocks, and in each of these blocks, some data from main memory which is being accessed would have been copied over here. Okay. So, given some access, let us say x1 to xn, we have different accesses, different locations, different blocks, let us say, that are being accessed. Now, depending on the order in which they are being accessed, they could be copied into one of these locations here. So, let us say some snapshot, we have x4 here, x1 here and so on. Okay, now xn is being accessed. So, before the reference to xn, I have some of these locations filled, some are empty, and when an xn location is accessed, I may put it in one of these empty slots. So, but you can see that they are not going exactly in order, that is, it is not being put in a particular block in the cache, is not really being used for a particular location as such, okay, or is there a particular order that we can have. Okay, so those are issues that we need to look at. So, I have particularly some blocks of data in fact, and different data can be brought and put into these blocks. So, where exactly do I put these blocks? Do I have some kind of a rule that I can follow, or can I put it anywhere that I want? Okay, these are different issues that we look at with respect to cache. Okay. So, given that I have some rule, I come up with different ways in which the cache can be organized. Okay. So, we will look at these different rules. Okay. So, I need to know where I need to put this data in the cache. So, I also need to know, once I have put it in the cache, where do I look for the data? So, I must have some kind of an identification of this is where a particular data has been put. Okay. So, these are different issues that we need to understand with respect to the cache. Okay. And of course, we said we will look in the cache, if it is there, it is a hit. So, first of all, how do I know if data is present in the cache? That is another important aspect to look at. Okay. So, how do I identify the data is there in the cache? How do I decide where the data has to be put in the cache? Okay. All these are issues that we need to understand with respect to organization of the cache. Okay. So, we will first take a look at one very simple organization which is called as the direct mapped cache. We will look at other organizations later, but we will start with this because it is a very simple technique. We have something called the direct mapped cache, where the location as to where exactly it will go into the cache is determined by the memory address. Okay, the address, that is, we know that data is being picked up from some address, right. So, you look at that address and use that address to determine where exactly in the cache it will go in. Okay. So, let us take this example. So, for instance, I have a memory with a number of blocks over here, and I have a cache with 8 blocks. Okay. So, these 8 blocks, you can see that there are different strips that are shown over here. These 8 strips are shown here which represent 8 different blocks, let us say. Okay. So, when I bring data from one of these memory locations, okay, you can see that I have kind of color coded them here. The ones that are light blue in color are the ones that will come into this position, into the second position. The ones which are, say, dark blue in color are the ones that will come into this position over here. Okay. So, which means that certain memory locations will be mapped onto certain block positions in the cache. Okay. So, memory blocks here, so memory also is divided into blocks, cache is also divided into blocks. So, I need to bring one block from here into this. So, which are the blocks which will come into a particular block in the cache? That is determined by the memory location, okay, the memory address. Okay. So, how do I do this mapping from this memory address to this address? It is very simple. All I do is I take the block address, the memory address, okay, the block address in memory, and I do a modulo operation with respect to the number of blocks in the cache. Okay. So, let us say, for instance, I have here 32 blocks, let us say I have here. So, all I will do is I will do an operation which is 32 blocks, right, totally. So, 32 mod number of blocks in the cache, which is 8. Okay, number of blocks that I have is 8. 32 will be the number of blocks, sorry, the block address I will take. So, let us say the block address is 1. So, I will do 1 mod number of blocks in the cache, which is 8. So, when I do 1 mod 8, the value I have will be 1. So, it will go into cache block number 1. Okay. Similarly, you can look at 9 mod 8. Okay. So, 9 mod number of blocks in the cache. So, 9 mod 8, again 9 mod 8 is 1. So, that also will go into block number 1. So, you will take the block address in memory and do a modulo operation on that with respect to the number of blocks that you have in the cache, and whatever value you get. Remember, modulo operation is nothing but the remainder that you get after doing a division. 9 mod 8, I am doing 9 divided by 8 and I have a remainder 1. That 1 will be the value of the mod operation. So, 9 mod 8 will give me 1. So, I know that it will now go into block number 1. So, this is what we do. The number of blocks typically, now we have the number of blocks as a power of 2. So if it is a power of 2, then this modulo operation that we need to do becomes very simple. Okay, we are familiar with doing modulo operation with powers of 2. So all therefore I need to do is I can use just the lower order address bits. Okay, so if I have 8 blocks in the cache, then the last 3 address bits are enough for me to identify which is the block that it will go into, because remember 8 is 2 power 3. So when I do a mod with respect to 8, the mod value will be in the last 3 bits. So last 3 bits, so for instance if my address is 11101, if I do a mod 8 operation on this, okay, with respect to the bits that I have here, the lower order 3 bits 101, that will be the block that we will map into. So you can see that this blue block here will go into block number 101, which is shown over here as the blue block here. Okay, so you can see that in this case I think I have taken 1, 2, 3, 4, 5, okay, 6, 7, 8. There are 8 such groups of 8, 1 8 here, another 8 here, another 8 here, another 8 here. There are 4 blocks of 8 that are shown over here. So you can see 8 into 4 you have 32 here, and you have 8 blocks over here. So for every 4 blocks you will find that there is one mapping that will come over here. Okay, that is the mapping that you are seeing here. So you can see here this block will come here, next this 8th block here will come over here, next this 8th block will come over here, next this 8th block will come over here. Alright, so position number 1, position number 9, position number 17, and then 25. So all these will map onto this position, the same position 1 over here, because of the modulo operation. So this is what we do in direct mapped cache. Okay, the simple mapping technique that we use. So all we have in this mapping technique is that you will do a mod operation of the block address with respect to the number of blocks in the cache and map it into this position. So once you've done this, your identifying where a particular block will go in the cache becomes very simple. Okay, so this is what we do in terms of mapping. Now that I have put it over here, and we see also that there are 2 different fellows who can map onto the same position. So how do I know whether it is this fellow who is sitting here or this fellow who is sitting here? Okay, these are other issues that we need to now look at. Okay, so we'll take a look at how we identify which block is present here and so on in the next session. So we will stop with this for today's lecture. So to summarize, so what we've looked at today is the idea of the memory hierarchy, and most importantly we looked at the principle of locality. So we talked about spatial locality and temporal locality. Spatial locality is the fact that it gets, if a memory location is accessed, one which is next to that is going to get accessed immediately. Temporal is that the same location is likely to be accessed frequently. Then we talked about the idea of the cache, which is a fast memory unit, and we talked about a hit in the cache and a miss in the cache and what happens in these 2 cases. Then we looked at one particular organization of the cache called the direct mapped cache. A set of questions to review the contents of today. Question number 1, in the memory hierarchy, which has the least access time? Question number 2, why do we have a hierarchy of memory devices? Question number 3, what is the principle of locality? Question number 4, what is cache hit ratio? Question number 5, what is miss penalty? Question number 6, if a cache has 4 blocks and the memory has 16 blocks, which cache block would memory block number 13 map onto in a direct mapped cache? Thank you.